that is into the study of the evolution of the oceans and fluids in general. And at the end, I will sort of offer an invitation for people to come and sort of get involved in the activities that I and my colleagues lead in this area. So let me start to say a little bit about fluid dynamics models. And this is a page which I borrowed from one of my previous talks, and the statement that fluid dynamics models are massively important, it's an understatement, because essentially everything around us and within us is about fluids. We all live at the bottom of a massive ocean of air, which obviously fluids. We live next to the oceans. Under the crust, there's a fluid core. We are made of fluids. It's hard to think of any human activity that will not involve fluids in one way or another. But the points that the bullet points that I have in here, the 2 bullet points, are related to essentially modeling the evolution of the atmosphere and the oceans. And I have here some satellite imagery taken from NOAA. This imagery shows 2 hurricanes. You can see them in here. They are called Lester and Madeleine. This was this happened in 2016 between 31st of August and the 2nd of September. And you might be able to see here this small green dot in here, and this is Hawaii. These are the Hawaii Islands, and people at the time were very keen to find out, as with any hurricanes, not just with these ones, when are they going to make landfalls? And you might hazard a guess whether they made landfalls, if either of them made landfalls. And if you look long enough, then you'll see that even this one, the closest to Hawaii, just about misses the islands. I mean, it gets into a storm, but it just about misses the Hawaii Islands. Now, the one thing on top of just by looking at this and trying to enjoy, what you need to look at, what happens to the clouds. The clouds obviously are markers for the evolution of the air. So we see these vortices that are the hurricane. We see the sort of the eye of the hurricane and things moving around. If you think of sort of the scale that this is the entire Pacific Ocean, things are moving quite fast, rotating as it were. Okay, so this is satellite imagery. This is data, right? And there's the question that you want to answer is, how do you use this data? How do you use this data to produce forecasts, to produce numerical weather prediction, and to try and model climate? And I put here on the right-hand side of my slide, I picked it up yesterday from the BBC website, the forecasts, the forecast for the UK yesterday. This happened yesterday, and obviously there's different forecasts today because the storm Christoph is upon us, and things are quite different. So there must be some connection between that data, the satellite data that I just shown you, and this forecast that is dished out by dished out by operational centers throughout the world, and other research centers that look into climate modeling. So yes, there is the connection, and in order to be able to make these connections, you need a massive computational capabilities. And you may not know this, but just to give you an idea of how much computational capabilities are required to get these forecasts, I have here the details of the Cray XC14 supercomputer that is used by the Met Office to produce forecasts. Some of the numbers are really staggering. It's the supercomputer is able to do 14,000 trillion calculations per second. It has 2 petabytes of memory, 460,000 compute cores, and so on and so forth. Now, the model itself, and I'm going to come back to the model. The Met Office uses a model, and I'll explain a little bit about the model. Has dimension of order 10 to the power 9. Right, so there's order 10 to the power 9 variables that are used in order to produce forecasts, and the observation space, right? So this includes satellites imagery, the one that I showed you, but not just that. Aircraft observations, ship observations, many observations, weather stations observations. These are of the order 10 to the power 7. So indeed, it is a humongous task to try to get a model and get a numerical simulation, but on a system with this dimension and using these observations to try to get the forecast that we see every day, day in, day out on our TV screens. Now, I thought I should compare this with the kind of a typical server station, and that's a server station that was used by one of my research associates, and we call it the beast. And it's a beast because it's really, as far as server stations are concerned, when we got it, it was really quite top of the range. This one only has 2 CPUs. With a total of 32 logical cores. Make a comparison with what's above. It does have 2 graphic cards, and we did use them quite extensively. Only 64 gigabytes of memory. Look at that. And we did do simulations. We did do numerical simulations and solved systems that didn't have 10 to the power 9 dimensions, but they did come close to 10 to the power 6 dimensions. So three orders of magnitude lower than that, just by using a single server station. And we weren't able to process 10 to the power 7 observations, but just 162 observations. But nevertheless, you can see that they scale quite favorably actually, compared to the massive supercomputer at the Met Office. Okay, so when you talk about transforming data, observational data, into forecasts, well, the first thing that you need to start is to start with a model, and the closest mathematical model that can be explained to a certain extent that is used by the Met Office, and not just by the Met Office, every other operational center around the world. These are called the primitive equations. And I didn't put them here to just go through them, because it probably will take a few days to go through each of these equations. I just put them there to see that it's not an easy model. It's not a straightforward single equation that is used. And then what one has to do, you have to take this equation and then implement it. And the implementation of this equation leads to a numerical model. and this is called the global circulation model. So, you might want to use your Google and try and find out what is the global circulation model. Essentially, this is the actual model implemented by the Met Office and all the other offices around the world that will give you a forecast that can be used to model the evolution of the climate. And just to give you an impression of the complexity of the model, what you do, you discretize the atmosphere, you discretize the ocean, you discretize the cryosphere. So that's the ice that you have around the Earth. And then you also discretize, you get a mesh for the land surface. So you have these four different portions, four different parts of the planet, which are discretized. And depending on what you want to do, if you want just a localized forecast or a global forecast, if you want to have a short-term forecast or long-term forecast, the type of the size of the discretization, the mesh of the discretization can be smaller or bigger. And so for each point in that mesh, you have to have the associated velocity of the wind or the sea, the associated pressure, the associated temperature. For each of these points, you have a whole lot of parameters that you get in there. And then when you put all of this together, you obtain a system of order, as I said, 10 to the power 9. So that's the model. That's the thing that is run on these big, massive super Cray computers. Okay, now what I want to do, I want to get something which is a lot simpler, right? And this is the Euler equation. Now, you might ask the questions, well, hang on a second, you are cheating here. They do all of this complicated equation. You do this one-line equation in here. To a certain extent, that's right. This is a lot simpler than the one used by the Met Office. However, the primitive equations and any other fluid transport equation that's out there is more or less a variation of this equation. It is an extension, a perturbation of this equation. And the point is, once you understand what to do and once you understand the difficulty of this equation, transferring to more general equation is not very easy, but it's possible. So for any budding mathematician out there that wants to start with something, that wants to start studying fluid dynamics, the Euler equation is the starting point. Well, having said that, it's not it's not the case that the Euler equation is simple. It does look simple in here, but it's actually quite complicated. And believe it or not, to this day, we don't yet know whether the Euler equation has a global solution in 3D. In fact, there's a prize for anybody that can show whether this equation has a unique solution, has a global solution, or indeed, for sure, it has only a local solution. So, and it's been bugging mathematicians for a long time, and it is something of an open problem which sort of everybody dreams of proving. Let me just go over the equation. So this is an equation which has as unknown, as a variable, the velocity of the fluid. So that thing that you saw in there, the evolution of the velocity is the evolution of the velocity of a fluid is the solution of this equation. Okay, but there's an additional unknown here, and this is this P here, which is called the pressure term. And I'm stating in here with this additional condition in here, which is called the incompressibility condition, which says that the divergence of the velocity is equal to 0. So in effect, what you have in here, we have not just one equation, but two equations, right? And therefore, it's natural to expect that you will end up with not just one, so not one variable here, but two variable here. But this variable, the first one, the velocity, in 3 dimensions, the velocity obviously has 3 components, v1, v2, v3. And then there's a pressure. The pressure is a scalar. And I'm writing here the gradient of P, which is just a vector. I put here T to signify that this is a vector, the column vector, not a row vector, which just takes the 3 partial derivatives of P in there. So the equation looks like this. What you have, what you have in there, the derivative, the rate of change for the velocity, plus here, this is an inner product between these 2 vectors. So this is the velocity field, and here, this is the gradient of V, plus the gradient of P. This is equal to 0. So that's the Euler equation, right? And because I have 3 components, I could write it in coordinates. So I'll have here 3 equations. So this single line here is in fact encompasses 3 equations, 1 equation for each of the 3 components. Okay, and you add to this, this additional constraint that the divergence of V, which is written in here, is equal to 0. And this is an incompressibility condition, which simply says that your fluid, you cannot compress to fluid. If it goes somewhere, this fluid, it has to come out. So that's sort of heuristically what this incompressibility condition is. So what I'm going to show you now, I'm going to show you a simulation. So this is just a numerical simulations of Euler in 2D in a box. So when you think of, we have a 2D fluid which is forced to remain in a box. Now here on this side, what it is in here, what you have in here is just the velocity, right? And the color means that, if it's dark blue, it means that there is no velocity at all. The velocity has magnitude 0, and the more towards red you go, it means that the velocity is has higher and higher magnitude. There's more. I hope you can see that there's some arrows in here that basically show the direction of the velocity. So it's not just the magnitude that you can draw up from these pictures, but also the direction of the velocity as well. And surprise, surprise, you can see these vortices in here going around, right? The fluid goes around. So, you can see that this is beginning to look very close to the 2 hurricanes that we've seen on the previous picture. And it's sort of not unexpected, because essentially, yes, we expect the atmosphere to behave more or less like to follow the Euler equation. So that's one thing. Now, what is there on this side? On this side, you have the vorticity. So the vorticity is a component which is connected to the velocity, and I'm going to show you the definition on the next slides. Basically, this one shows how quickly does the liquid, the fluid, rotates among itself, right? So it measures how quickly you turn around, the fluid turns around itself. And if it's white, that means the fluid doesn't turn around itself at all. And if you go towards the blue one, it turns around in one direction, in sort of in the clockwise direction. And if it's brown, it turns around in an anti-clockwise direction. Okay, so these 2 components are really connected to one another, and in effect, for an incompressible fluid, you can get the velocity out of vorticity, and vice versa, you can get the vorticity. You can get the vorticity out of velocity, and you can get the velocity out of vorticity. Right. Okay. So I've shown you here the Euler equation. And why is the Euler equation difficult? Well, it's like a transport equation. Essentially, you transport velocity in here, but it's non-linear, because you get this product between the velocity and its own gradient. And then you ask the question, well, so what? So what? Why would a non-linear equation make things very difficult run? And the answer is because essentially things could behave very, very badly. So you have to, so think about, suppose, your rate of change here, right, will depend on this inner product. And suppose you have the velocity in some sense going alongside this gradient. So the rate of change might increase quadratically because of this product, right? And it's actually quite difficult to try to visualize this, to try to heuristically understand why this happens. And the reason for that is that the human brain is used with things that are constant. It's used to things that increase linearly. We are getting to grips with understanding what happens when things increase exponentially because of the current pandemic. But this is super exponential, right? So this can lead to a super exponential increase. By the way, I'll show you lots of numerics here, and all of these numerics have been done by our excellent research associate Wei Pan, who works with us on a related project. So in order to show you exactly what sort of nonlinear behavior we can expect from an equation like that, I picked up a short movie from the YouTube. So let me just run this for you. So what you'll see in here, these are some columns of smoke in here, and then you see very quickly there's going to be a line. There's going to be a plane going past this tower, and for a long time things will behave quite normally. Of course, there will be some perturbation in the columns of smokes, but not something which is out of the ordinary. But give it enough time, give it time for the nonlinearity to kick in, then what's going to happen, and you'll see this very shortly. All of a sudden you'll see some sort of speed up out of nowhere. There will be a speed up of the air. Okay, so we are still here. They are still parallel, but they're beginning, something is beginning to happen. But now all of a sudden right here you see this speed up in here. That's really a clear sign of the nonlinearity of the evolution of the atmosphere, and everything then goes badly afterwards. Okay, so let me go back here. So the velocity, this equation is really the basis of many fluid models, and it's hard because it's nonlinear. Okay, so what do people do in order to try to cope with such a complicated equation? Well, essentially, they get higher and better computers. So, I mean, the plan is that by 2040, 2050, that grid that I was explaining earlier will have a mesh size between 10 and 100 meters. So, you think about how many points you will need to cover the planet with points that are a distance from one another 10 to 100 meters. And then on top of this, people will use more and more better and better observations. The satellite observations will be better. Okay. Having said that, at the moment, 99% of the observations are discarded. So it's just about 1% of the observations that is used for reasons that I don't want to go to. Obviously, we can discuss that separately. So the answer that the community has to this complicated equation is to throw in more computational effort. What we want to do, we want to go the other way around. So rather than having more refined computations, we want to go and have coarser grids, but try and add stochasticity to the models, right? Try to make the models uncertain in such a way so that these perturbations, these hidden differences between the coarse resolution and the refined resolution is modeled by this stochasticity. And I've written here, these really 5 bullet points that kind of explain what we plan to do, right? And I'm going to come back to this. But for these talks, all I want to do is to explain to you how do we add stochasticity, because there's many ways in which you can add stochasticity, right? But what we want to do is to add stochasticity in a meaningful way, in a physically meaningful way. And so that's what I'm saying here. We incorporate uncertainty into the model. And I have here a quote from Donald Rumsfeld, which some of you might or might not know about him, right? I'm not going to go over to quote. Obviously, you can go and can read the quote, or use your Google to find out about this. But the point of this is that what you want to do, you want to add stochasticity to model things that you cannot capture by the deterministic model. So rather than trying to make this deterministic model more accurate, you'll say, okay, we're gonna accept the fact that you're never gonna be able to get this deterministic model precise and completely accurate. We're gonna incorporate stochasticity in order to model this uncertainty. Okay. So the question is, how do you add stochasticity? Okay, so why do we want to add stochasticity? Well, we want to add stochasticity because rather than simulating things on a refined scale, so this is the simulations that you've just seen on the previous page, we want to simulate things. For example, we want to simulate Euler on a coarser scale. So, you can see here, the two simulations start from the same initial conditions. Of course, one is a coarsening of the other one, but gradually and quite quickly, the two simulations begin to look quite different. So, if you look at the vortices, they are in different place. If you look at the this estimate of the vorticity, it's really quite different from the other one. So by coarsening, you actually lose information, and you lose information quite quickly. And what we want to do, this loss of information, we want to model, not precisely, but from a probabilistic perspective. So that's the point here, is that we want to add stochasticity not to get a better pathwise estimation of the simulations on the refined scale, but to model the distribution of this loss of accuracy. So how do we want to do that? Well, rather than just taking the PDE and blindly adding some stochastic term to the PDE, let's think about what's happening in there. So, in the simulation, you have loads and loads of particles of fluid. That's what they are, particles of fluid that evolve according to the velocity field, right? And this is sort of an ODE. So what we say is, okay, take this ODE and make this ODE stochastic. Add stochasticity to this ODE, transform the evolution of each of these particles of fluid into a stochastic evolution. Perturb this stochastically. Okay, so if you want to see a picture of one particle of fluid, so what you see in here is the same simulation, but I'm looking at this particle of fluid. So if you look at how it evolves, it's amazing. If you haven't seen this before, it's really amazing. You get the feeling, sometimes it slows down, sometimes it goes faster. Really, it's a very chaotic evolution. And the plan is that you take the evolution of this particle of fluid and you say, right, I'm going to perturb this evolution. So I'm not going to perturb the PDE itself. I'm going to perturb the evolution of the particle of fluid, and then I'm going to ask the question, where does it lead? What is the resulting SPDE that models these massive stochastically perturbed particles of fluid? Okay. Now, this idea was exhibited, was presented in a paper by our colleague Daryl Holm in 2015, and it has deep physical connections, in particular in relation with variational principles for stochastic fluid dynamics. You know, if you guys know about this, it will be worth looking at it because it really led to a lot of developments in this area of SPDEs. And just recently, in fact, the paper has just been accepted this week. My student and I have produced a generalization of that, where the array of perturbation it's much wider than the one that Daryl has presented in his paper. Okay, so I'm going back to my Euler equation, and what I'm doing now, I'm writing the equation in vorticity form. So rather than going and presenting what happens to the velocity field, I write the equation and explain what happens to the vorticity, to what's on the left-hand side of the picture. But before I go into this, let me just have a quick breakdown and then sort of let Inquiry ask people if they have any questions. No? I'm trying to get back to...
Yeah, sorry. Apologies. Thank you so much, Dan. So if anybody has any questions, if you'd like to raise your hand now, we can take any questions from the audience directly. And I have one question that's come up online. Would anybody like to ask anything at this point? Okay, so while we're waiting for any other questions at the moment, maybe I'll read this one from online, but apologies, I'm having a little bit trouble reading it. It's got a subscript, so I can't see it. But what's the gradient of V? Sorry, I can't see what it is here, as V is three-dimensional. Hopefully you...
Excellent question. Excellent question. Right. So let me go back. So you can see it here when you write it in components, right? So what you do is when you get the say you look at component 1, so you take I equal to 1, right? When you take I equal to 1, then you put the gradient here. You take the gradient of V1 in here, right? So you take the sort of partial derivatives with respect to V1, and then inner product of that with V itself. And then you do this with V2, and V3. So for each of the 3 coordinates, you take the gradient of the corresponding coordinate of V.
Thank you. Any other questions at the moment anybody would like to ask? Feel free to raise your hand. Yeah.
If not,
there's one more that's come up here online. Is there anyone working on machine learning and stochastical differential equations at Imperial? But maybe that's something that we can look at the end. It's more of a general question.
And yes, there is work, but we can talk this offline. It's not directly related to the talk, but the answer is yes. And I'm spending a lot of time talking to machine learning people to try to do exactly this. Okay, so let me go on. So what did I do so far? I explained my motivation. I explained why am I looking at the Euler equation. I explained how I'm introducing noise into the Euler equation through perturbing the evolution of these particles of fluid. And now I'm going to show you what is the result. And the result is extraordinary because if you were to look at the equation itself, it would be quite difficult to realize that the perturbation looks that complicated. So something, just by saying that we're going to perturb the particle of fluid leads to this type of perturbation. Okay, of course you're going to ask, well, why don't you try something simple? Why do you go to things that are so complicated? And the answer is yes, you can try additive noise or you can try multiplicative noise, but the answer is that these perturbations are not physical in the sense that the sort of natural conservation laws are lost if you use different types of perturbation, right? So essentially what we're saying in here is that if you want to be physical, if you want to have meaningful stochastic perturbation, meaningful models for uncertainty in the model, that's what you need to do. Okay. Now, I'm not going to go through a lot of these things. I'm just going to point out the sort of main properties of these types of perturbation. So what is this perturbation? Okay, so as I said that we're looking not at the velocity field, but at the vorticity field. And in 3D is not one-dimensional, but is three-dimensional, and is given as the vector product between the gradient and the V. So, by definition, we're looking at this. So that's the vorticity field. And so the equation looks like this. These square brackets here are defined in here, right? So, it's an operator, it's a bilinear form, it's a differential bilinear form between V itself, the velocity field, and omega. And remember, this V in here itself depends on omega. So it's not like it's an independent quantity. So this is a nonlinear term. Okay, so if you were to forget this, that's what you would get if you take the curl of the velocity equation, of the Euler equation in velocity form. And then you get this term in here, which is stochastic. And it's stochastic because it's essentially written as an integral with respect to some Brownian motion. So the model for the stochasticity is written here is in differential form, is a sum. I'm writing here infinite, but in practice is always going to be finite, of some integral with respect to Brownian motion, where inside the integrand you get essentially the same operator that you had in here, except you replace this V by disk size. And disk size are coming from where? Well, disk size are exactly the size that you use to perturb the particles. Okay, so that's the plan. That's the point in here, that somehow this looks very similar to this equation in this case, exactly because I preserve the evolution of the particles and perturb them stochastically and not perturb directly the PD. So this becomes now an SPD, which I keep the same constraint, incompressibility constraint on the omega and some initial condition. And in here, when you try to analyze mathematically the solution, you assume that the solution belongs to some space. First of all, the underlying space is the torus. That makes things very simple. This is a three-dimensional torus. And what you look for solutions that are in this oblate space. So that simply means that the solution, its derivatives of first and second orders are all square integrable. So that's what this means. So we're looking for solutions of this for which the solutions are in L2, and so are the first order and second order derivatives. Okay. Now, there's one more thing which, this only people that work in stochastic analysis will understand. This type of integrals is written here in differential form. That's why you don't see the integral sign. This type of integrals are Stratonnovich integrals, and you can transform them into an Ito integral, and it's going to look like this. This transformation incorporates an additional term in here, right? Which I'm not going to go into it. It's sort of very standard transformation from Stratonnovich to Ito. Good. So we found, the physics told us what the solution, the SPD should look like. Now we put our hat of mathematician on, and we ask, is there a solution to this? And yes, there is. And if you want to see the details of this result, the paper appeared in 2019 in Journal of Nonlinear Science, and is joint collaboration between myself, Franco Flandori, and Daryl Holm. So let's see what we can say about this. So what we can say is that yes, there is a solution. In other words, there is some field that has these properties defined on the torus. It's square integrable together with derivatives of first and second order, right? But it's only a local solution, and by that we mean that we can only show that is a solution up to some time, up to some stopping time. Okay, now you might say, well, that's we don't like this because you want to see a global solution. Well, we can't, because should we have been able to do that for this particular SPDE, that would have meant that we've done this for the deterministic version as well, because you just take this size in here to be equal to 0, and you get the deterministic PDE. So in some sense, this theorem in here incorporates the deterministic case. And should you have a global solution here, then obviously you have a global solution for the deterministic case as well. But what is important here is that there is a characterization of the blow-up time. Okay, so what is the blow-up time? This blow-up time, so you say, okay, there must be some maximum time, some maximum stopping time up to which you have your solution. The solution is well defined. Now, it may be that this maximal time is infinite. It may be that you have a solution over the entire positive half line, and then that's fine. You have a global solution. We're done. We've proved our millennium problem. We got the $1 million in our pockets. But if that's not the case, if your stopping time is finite, what can you say? What happens there at that point? So that's this amazing criterion, which holds true in the deterministic case, and we prove that it still holds true in the stochastic case. And it's perhaps the only equation, the only stochastic PDE that I know of that has this characterization of the blow-up time. And it's not surprising, because essentially it should behave, it should satisfy, it should inherit all the properties of the deterministic version. Okay, so what this says the following thing. So if this blow-up time, this maximum time up to which I can construct my solution in this space is finite, then if I integrate what? The supremum norm. So this is the supremum norm of the vorticity. Okay, so I don't care about it not being differentiable. I don't care about it not being twice differentiable. I only look at the supremum norm. So if I can integrate that from 0 to tau max, and this is going to be plus infinity, then that's my blow-up time. So all I have to do to decide whether I have a blow-up time or not is to look at this integral, which I can compute numerically. And then if it turns out that this explodes, we're done. We found out we found that the maximum, we found out that the stochastic version of Euler equation explodes in finite time. It's a very nice equation. It's a very nice criterion, and it's really sort of a unique. It's sort of unique among many other SPDs that are out there that are not of the same form, that use a different stochastic perturbation. Okay, so I don't want to go into this. I promise Ingrid that I leave 10 minutes on the end. I wanted to tell you a little bit about how I prove this. There's some nuggets of proof, some nuggets of beautiful ideas, both in showing that the solution is unique and in showing that there exists a solution. Just 1 minute to say is that, so in order to show the existence, what you do, you perturb the nonlinear term. You introduce a cutoff function for the nonlinear term, and that's still not enough to try to show that the solution. You add a viscosity term in here. So this is the Laplacian. If I didn't have a 5 in here, this kind of would be just a sort of a Laplacian term. Normally, just by adding a Laplacian makes the solution very nice, and very well behaved. Well, it turns out that at least for using the tools that we developed for the paper, we had to go much higher than just the Laplacian. We had to use a super viscosity term, delta to the power 5. And then you have a solution of that. Then you take this to 0, this viscosity parameter to 0, and get the solution. Okay, so there's been a lot more work after that. I'm not going to go into that. I'm just going to add one more thing, which sort of it's an invitation for students to come and join us, to come and follow what we have been doing in this project that I and my collaborator Daryl Holm, Bertrand Chaperon, and Etienne Memin are leading. So this is a project dedicated to stochastic transport in the upper ocean dynamics. There is a website here, and you don't have to sort of copy this down. Just type Steward, STUOD, into your Google or your any browser, any other search tool that you have, and you'll find this website. We have received funding from the European Union to try to use SPDs in order to effectively carry out a program that will end up with doing exactly the things that I showed you and that I announced, that we want to increase our understanding of the evolution of the ocean to try to produce better forecasts by adding stochasticity. And there are lots of ways in which you can interact. Our doors are open, literally. We have annual conferences, monthly sandboxes. We get students to talk to us. And there's an activity that's coming up. And if you follow the website, you will see an announcement shortly by the end of this month. It's a hackathon, which we plan to run at the end of March, which if you want to take part and try to solve some of these problems with our guidance, you are welcome to do so, and there will be a registration form on our website. Okay, so I'm going to stop here, and I'm going to go back and let Inquiry lead the question bit. Thank you very much.
Thank you so much, Dan, for that, and especially also encouraging students to join and follow the group. That's fantastic, and then the hackathon sounds excellent. So hopefully a lot of the students here will be encouraged and interested in taking part. There's so many wonderful opportunities there to learn from the group and the work that they're doing. Also, Dan, you mentioned Daryl. So just to plug, Daryl will also be doing an inspirational lecture. He'll be doing one on the 17th of February. So just plugging that as well. Okay. Yes.
Excellent. So now just to add on that is that sort of I'm giving you I discuss things from a sort of pure mathematician's hat on. Daryl will be more applied. He's from the applied section, and obviously it's going to be a completely different viewpoint. So I encourage people to attend his lecture as well.
That's
Thank you.
Excellent. Thank you so much. So we had a question during your talk. This was when we were on the slide, the 3D stochastic Euler equation. And the question was, does this equation improve the mean forecast?
Excellent. So right. I only told you how you introduce uncertainty. But of course, you will ask okay, you've done it. Now you convinced us this is the right thing to do. But now, how are we going to improve forecasts? Okay, so that is obviously the next step. And for that, we use tools of data assimilation. Okay, so there's a second toolbox that we need to use in order to get a better forecast. And we use something which is called a particle filter methodology that has to have this stochastic dynamical system behind this. You need, so it's a Bayesian methodology. So you have to know the distribution of your dynamical system before you start to use data in order to produce better forecasts, better than those that you would get if you were to use just deterministic models. Now, I can show you results, but not in the following 4.5 minutes. So the answer is yes, but I cannot show you anything at the moment.
Okay, so that's another lead to kind of look into it more and to join the discussions that the team is doing. Okay, we had another question online. What is the principal advantage of introducing uncertainty in the Euler equation? Does the fact that it is less restrictive make it easier to solve? And can the uncertainty around the true solution be arbitrarily bounded in a small time interval?
Okay, so another good question. So in order to improve forecast, we are all about forecast, related to the previous question. We use a Bayesian perspective. You need to have a description of your of the distribution of your system. So you need to introduce uncertainty. It's not like you can just use the deterministic procedure. Now, how much uncertainty do you introduce? So those size that you saw there, is not going to be up to us. These are not size that we plug out of the thin air. So you need to calibrate the system. You need to deduce this size from the data. So we cannot say that basically we just have a tiny teensy little bit of uncertainty added, and then that's going to be okay. No. The uncertainty, the amplitude of the uncertainty, the size of the uncertainty, once we find out what is the form, is dictated by the data. So it's not going to be, it's not like you say, well, you have a small cell, we just put a bit of uncertainty, we just have a small perturbation and that's that. No, this is not something which is decided by the observer, by the modeler. This is something which is obtained, extracted from the data. So you have to calibrate your system.
Great, thank you very much. Okay, we've got just a few minutes left. Does anybody else have any questions that they would still like to ask Dan at this point? If you want to just raise your hand, or you can ask it on the Menti, I'm happy to read out.
And I think your son wants to ask a question.
Yes, my daughters are coming in to ask.
Hello.
Okay.
All right. Okay, so in that case, I'll stop here. Thank you very much, and I hope to see you, some of you guys, at the activities of Steward, and in particular at this hackathon that's coming up at the end of March, and the details will be put on our website, and I'm going to ask Inquiry to post the details to all the students in the 4th year and all the PhD students.
Great. Thank you so much for your time this afternoon, for sharing your work.
Thank you very much.
Thank you, everyone. Bye-bye.
Bye.